Grade 10s, so today we are going to be working on understanding Newton's laws. So we're done with graphing and we're going to look at a little bit of how physics is applicable to your everyday life. So we'll start off, you'll notice that all of Newton's laws are in this one document together. We're not going to cover all of this today. We're just going to do a bit of a history and then Newton's first law. And then we'll cover this second part with the second law and the third law coming up next class or next week. So we'll start it off here talking about Aristotle. So he was in the 4th century BC. He's a Greek philosopher and believed that everything in the celestial world, so stars and planets, moved in perfect circles and at a constant velocity. So they're always traveling at, say, let's go 6,000 kilometers per second or whatever they're traveling at. And they always stayed at that, and they traveled in these perfect circles. So he believed that everything in the terrestrial world, meaning Earth, had a tendency to move towards the center of the universe. And at this time, the Earth was believed to be the center of the universe. So he called this motion natural motion. So basically just the idea that everything was centered around the Earth because, you know, humans are the center of everything. Earth must be the center of the world, or not just the world, Earth must be the center of the universe. Everything is coming towards Earth because we are central. And we know that's not true now, but at this time, this was pretty advanced thinking. He's sitting there trying to discover things about stars and worrying about all these sorts of things. So it's, as much as it's funny for us now to think, oh yeah, of course, the Earth was the center of the world, at that time that was pretty advanced and thinking about how things were even moving. So more related to what we're going to be talking about, he thought that any motion that was not up or down could only happen if a force acted on it. So he called this violent motion. So anytime there was force applied to an object, that would be considered violent motion. So violent motion would continue as long as the force was present. So as soon as the force was removed, the motion would stop. So this means if you rolled a ball, as soon as your hand left the ball, it would stop moving. So we know that this isn't true. So if you're pushing something with your hand and you stop pushing it, if you're rolling a ball, say, and you stop pushing it, that object doesn't necessarily stop right away. Some objects do, but if you give something a really good shove, it's most likely going to continue on after your hand has left that object. So we know that Aristotle wasn't quite right in his thinking. Objects do keep moving after a force is no longer applied. Okay, so this was kind of him setting a very good basis for us to disprove his theories and advance theories of motion. So Galileo came along next, and he was like, hey, you know what, I don't think Aristotle's right. I think Aristotle's things move. I can push something and it'll keep moving. I don't have to keep my hand on it. I don't have to keep a force applied to it. So he decided that an object does not stop due to the absence of force, but the presence of an opposing force. So it's not because I stop pushing on an object, it's because another force is applied to it. And so he basically came up with the idea of friction. So he did this experiment to come up with this idea. Now it looks a little bit confusing. So the idea is that if a ball starts here and rolls down an incline, it will rise up the opposing incline to almost the same height. So not exactly the same height, but pretty close. So when the incline was reduced, the ball had to roll further to reach that same height, but it did. And then again, decreasing the incline, the ball would have to roll further and further. So if there was no opposing incline, based on the idea, or based on what he'd seen here, that the ball kept rolling back up to the same height, this ball should technically roll forever, right? Obviously not. So what he realized is that some force has to be applied to this ball. So that force is friction. Again, if this ball rolled and got to the same height, and this ball rolled down and got to the same height, and this ball rolled down and got to the same height, technically, if there was a flat line or flat surface, that ball would roll forever. But it doesn't, because there's a force that's acting on it to stop it, which is friction. Okay, so take a minute to think about that and understand how the ball is moving and then how he discovered friction, okay? So after we had Aristotle saying that you needed a constant force and Galileo saying, no, 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 you just have friction, that will stop the object, it's not a constant force, we had Isaac Newton, who really came up with 3 laws that have yet to be disproven and that work with the ideas of physics. So we're going to look at just the first law for now, and then we'll look at the second and third laws later. So the first law of motion is an object at rest will stay at rest, or an object in motion will stay in motion unless acted upon by an opposing force. It's also called the law of inertia. It's just the idea that objects want to continue doing what they were already doing. So let's just imagine you're laying in bed, you just woke up, it's like 7 o'clock, I don't know, 7, 8, some people maybe 11. Anyways, so you're like laying in bed, nice and cozy, you don't want to get up and move. That we can think of as Newton's first law. So you want to stay at rest. An object at rest will stay at rest. When you're out, you're doing stuff, you just want to keep going, right? So that's obviously not exactly how Newton's first law works. It's more so if I have my computer sitting in front of me, this object's going to stay at rest until I come and pick it up or move it, okay? So if we think about this in terms of driving, all of you are going to be getting your licenses in the next couple of years, so that's exciting. If we're driving at a speed of 100 kilometers per hour on a highway, everything in that car is being acted on by the same 100 kilometer per hour force. So you're sitting in the front seat, you're traveling at 100 kilometers per hour. You don't slow down until you apply a force to your car and yourself. So when you're pushing the brakes of the car, that will start to slow down the whole car, and in turn, while the car starts slowing down, the car applies a force onto you that slows you down as well. Okay, so you're traveling 100 kilometers per hour, pressing on the brakes, the car starts to slow down, you start to slow down because the car applies a force to you, the brakes apply a force to the car. Now, if we think about this, if you were in a car crash and you were going 100 kilometers per hour, you would continue at that speed until a force caused you to stop. So the car itself, if we look at this kind of diagram here, this little guy on his motorcycle, he is driving along, he's going 100 kilometers per hour. Uh-oh, someone built a brick wall in the middle of the road. Not a great idea. So this force applied directly to his motorcycle. The force did not apply to him. Okay, so he crashed the motorcycle into the brick wall, but he himself had no force applied to him. So the car comes to a stop, but since there was no force directly applied to you, you will continue at 100 kilometers per hour until there is a force. So in this example, he is thrown off of this motorcycle, and until he runs into an object or gravity acts on him enough to cause him to run into the ground, he's not going to stop moving, okay? So when you're in your car, it's always important to have a seatbelt and airbags. So these allow a force to be directly applied to the passenger so that they're not thrown forward at 100 kilometers per hour. So you might run into the seatbelt and it might break your rib, or if you're sitting funny, it might break one of your bones, but at least you're not being projected through a windshield. Okay, so I hope that makes sense in terms of that object in motion, you the object in motion, stay in motion if you're not wearing a seatbelt until a force acts upon you to stop you from moving. So if I'm sitting there and I get ejected from the car, I'm going to keep traveling at 100 kilometers per hour until a force causes me not to. The car was hit and crumpled up because that force acted directly on it, but unless force acts directly on me, such as a seatbelt or an airbag, I'm going to keep moving at 100 kilometers per hour. So looking at this picture here, obviously no one was harmed in this photo. It says inertia, your truck has brakes, the massive hunk of stone doesn't. So try and explain using Newton's first law, what we just talked about, so the idea of an object in motion will stay in motion until acted upon by a force. Use that to explain what's happened in this image here. So if you have any questions about Newton's first law, let me know. We're going to continue on with the second and the third law next week.